Dear students, today we will talk about products of inertia. So, what is it? It's defined similarly as moments of inertia, but the product of inertia is made with respect to axis of coordinate system. And first we can calculate product of inertia with respect to axis xy, and the definition is like this. It is x by y dm over m, and similarly we can write or calculate product of inertia with respect to axis yz. dyz is then y by z dm over m, and finally with respect to axis z and x it is dzx z by x dm. Naturally, we take into account these coordinates of the mass element and we integrate through all volume respectively over full mass of the body. So we found that not only, or we can say beside jx, jy and jz calculated in previous video, we also have another mass characteristics of the body. We have other characteristics of mass properties of body, and they are dx y, dxz, dyz, and these numbers are called moments of inertia, and these numbers are called products of inertia. So we have 6 characteristics, 6 numbers defining mass properties of body, and we can write them in so-called matrix of inertia. Matrix of inertia. Usually we denote matrix of inertia as I, and it is 3 by 3 matrix. On diagonal there are moments of inertia jx, jy, jz. Above the diagonal there are products of inertia dxy, dxz and dyz, and this matrix is symmetric about diagonal. In accordance to definition of matrix of inertia, we must remember that we must add minus in front of every d. Okay, it comes from definition. You don't have to think about it a lot or much. Just remember that. So finally we can get this shape of matrix. In diagonal there are moments of inertia. Above the diagonal there are minus dy minus dz dz minus dyz, and symmetrically to the diagonal there is minus dyx minus dzx and minus dzy. It corresponds like this. Now you can ask, what is the difference between dxy and dyx? So it's very easy. dxy is equal dyx, dxz is equal dzx, and yz is equal dzy. It's clear, it follows from definition, because it doesn't matter on the order of multiplication. So dxy is x by y and dyx is y by x, what gives the same result. So this is the reason. And you can also remember as a mnemotechnical hint that you can imagine there is x, y, z, and in column there is x, y, z. So in diagonal it's x to x, it's jx. Here it's y to y, and here at this position it's z to z, and here it is x, y, x, z, y, x. So this is a principle how to distribute indices over the matrix. So once again, be careful. So if, for example, if dxz is 100, so this in matrix, in this corner, I draw it here, this corner is here, so I write minus 100. Okay, it's only formal aspect of denoting, and it's some consequence of more complicated calculus in future for more advanced study. Okay, so and we see it like this, minus minus. If we think what is the total characterization of mass properties of rigid body, we can answer the first, it is mass. So the body is defined by its mass. But it is not enough. We need also to know jx, jy, jz, so moments of inertia. We also need to know dxy, dxz, and dyz, products of inertia. And finally we have to know position of center of mass. Coordinates of center of mass. So this is a full description, total characterization of mass properties of a rigid body. So if we need to make complex dynamic calculus of rigid body, we need to know all these parameters. You can compare it with particle. If we have a particle with no dimensions or with negligible dimensions, so the only and simultaneously total characterization of mass properties of particle is only mass, because there is no dimension, so there is no mass distribution in space. So these are zero, these numbers are zero, and this is equal to position of the particle. So total characterization of mass properties of particle is only mass. But if we deal with body, where is some distribution of mass in space, we need to know all these numbers.